Welcome to ninth lesson in the chapter Conservation of Energy and Momentum. In the last classes, we have discussed about the conservation of energy, linear momentum and angular momentum. And we discussed these topics in the case of a single particle and for collection of particles. Here in this chapter, we are going to discuss an important concept called central force. And this central force is very important in the field of law of conservation of angular momentum. First of all, we will introduce what is a central force and then some properties of central force. And after that, some of the examples for the central force and the motion of particles in the central force in the real world situation. So the first topic is central force. Central force, as the name suggests, there will be a center for the force. So a force acting on a particle is said to be central if that force is acting towards a point or away from a point. That fixed point is called the center of that force. That is one of the conditions for the central force. That is, the force should be directed away from a point or towards a point. And another condition is the magnitude of force acting on the particle depends only on the distance between the center and the particle. So if these two conditions are satisfied, then the force is said to be a central force. So mathematically, a central force can be represented as F is equal to F of R. That is a function of the distance of the particle from the center of the force, and R cap, it is a unit vector connecting the center of the force to the particle, where F of R is a scalar function of the distance R, because we said that the central force, the magnitude of central force, it is represented by F of R. It depends only on the distance. It means that it may depend on the medium between the two particles also. That will be discussed in detail when we are dealing with the individual central forces. But for the time being, we say that the central force depends on the distance between the particle and the center, and R cap is a unit vector in the direction of the center to the particle. So R cap is equal to vector R by magnitude of R, where vector R is the position vector of the particle with respect to the center of the force. So examples of this central force are very famous. Electrostatic force is an ideal example for central force. In electrostatic force, by Coulomb's law, we have seen that the force acting between two charged particles, F is equal to 1 by 4 pi epsilon 0, Q, that is Q1, Q2 by R square. One of the charge is Q, the second charge is capital Q by R square. R is the distance between the into R cap. For example, in the case of a hydrogen atom, and there is a nucleus having plus E charge and there is an electron having minus E charge. So this electron is revolving around the nucleus because of this attractive force, and this attractive force is always directed towards the center of the nucleus, and the magnitude of that attractive force depends only on the distance between the nucleus and electron. So electrostatic force is an example of central force. Another example is gravitational force. For example, the sun-planet system. If we consider the planetary motion around the sun, we see that sun is placed at one of the foci, that is, it is at one focus of the sun, of the orbit, and the planet is revolving in elliptical orbits with the sun at one of the focus. So here also, the gravitational attractive force on the planet is towards the center of the sun. Always it is acting towards the center of the sun, and the magnitude of this attractive force depends on the distance between the sun and planet. Of course, it depends on the mass also. If we keep the planet and the sun mass are always constant, so we can say that the force of attraction depends only on the distance between the sun and the planet, or between the center of the force and the particle. So this is also an example for the central force. Another example is the elastic forces. For example, the famous force in the case of a spring, which leads to the simple harmonic motion, F is equal to minus kr into r cap. Here also the force is depending, the magnitude of the force is depending on the distance r of the particle from some equilibrium point. So this is an example for the central force. We see that the gravitational force, there is a negative sign, it indicates that the force is always attractive. And here also there is a negative sign, it indicates that the force is always directed towards the equilibrium position. And in this case, this may be positive or negative depending on the charges Q and Q. If both of them are positive or negative, then the force will be positive, it will be repulsive. If one of the charge is positive and the second one is negative, as in the case of electron nucleus system, then the product QQ will be negative and the force is negative. Negative means it will be attractive. So the force may be attractive or repulsive, but electrostatic force, gravitational force, elastic force, all these are examples of central forces. Now, one of the property of central force. If a particle is moving under central force, the torque acting on the particle, T is equal to, as already we have studied, it is equal to dj by dt, where j is the angular momentum. Now that is equal to r cross f. Torque is equal to r cross f. That is equal to r cross of, now f is central force. It can be written as f of r into r cap. Now this f of r is a scalar function, so it is not operated with the cross product. So we can take it f of r, then remaining will be r cross into r cap. Now r cap is actually vector r by magnitude of r. Now r cross r is 0 because r cross r is r into sine 0. So it will be equal to 0. So the important property of central force is the torque acting on a particle moving under the influence of a central force is equal to 0. If torque is equal to 0, then the angular momentum J is equal to r cross mv will be a constant. So this is an important property of the central force. Angular momentum of a particle moving under the influence of central force is conserved. The angular momentum conserved means angular momentum J is a vector quantity. So it is a constant, means it should have a constant magnitude and direction. So it is, angular momentum is perpendicular to both the position vector r of the particle measured from the center of the force and velocity of the particle. So as J is perpendicular to both r and v, and J cannot change its direction, we can say that r and v should be kept in the same plane, so that J is always perpendicular to the plane containing vector r and v. Or in another way, we say that the particle moving under central force should move in a plane, or the orbit of the particle should be in a plane. So the motion under central force is a two-dimensional problem. It is not a three-dimensional problem as we expected. It is a two-dimensional problem. All planetary motion around the sun is two-dimensional motion because they are moving in a plane. Their orbits will be lying in a plane. It does not mean that the orbit of all planets are in the same plane. There may be different planes for different orbits, but for a given planet, the orbit of that planet should be in a plane. Now the second one is the concept of areal velocity. Let what be the center of the force, and suppose a particle moving under the central force is moving from a point P to a point P dash, and at the point P the position vector of the particle is r. At the point P dash the position vector is r plus delta r. The particle is at the point P at a time t, it reached the point P dash at time t plus t dash. So the position vector of the particle changes from r to r plus delta r. So this vector is r and this vector is r plus delta r, that is final position. So this vector along the arc of the circle will be the change in position delta r. So the area swept out by the radius vector, that is this shaded area, the area swept out by the radius vector in a time delta t is equal to the area of this shaded region, and it is equal to half into r cross delta r, because r is one of the side and delta r is the second side. So r cross delta r will be the area of the parallelogram with the sides r and delta r, but we are required to find the area of this triangle. So area of that triangle is equal to half into area of the parallelogram. So that is equal to half into r cross delta r. Now this area delta S is swept out by the particle in a time delta t. So dividing both sides of that equation by delta t and taking the limit delta t tending to 0, we see that the limit delta t tending to 0 of delta S by delta t, it can be called as mathematically as ds by dt. It is the area swept out by the radius vector in a time dt. That is, it is the area swept out by the radius vector by the time taken. Or we can say that it is the area swept out by the radius vector per unit time. This area is called the areal velocity. It is velocity per time. Areal velocity is the area swept out by the radius vector per unit time. So that is equal to half into r cross of delta r by delta t. So that is equal to half into r cross v. Delta r by delta t is the velocity of the particle moving under central force. Now m into r cross v is the angular momentum. So r cross v is angular momentum by m, that is j by m. So this quantity will be equal to j by 2m. As already we have seen that angular momentum of the particle moving under central force is a constant. So it means that the areal velocity of the particle is a constant under central force, or the area swept out by the radius vector of a particle moving under central force is a constant. So this is another important property of the central force. Now an example for the central force, it is the planetary motion or satellite motion. The planets move in elliptical orbits around the sun at a focus. So the gravitational force on the planet is directed towards the center of the sun. This force is central force. So the angular momentum of the planet should be a constant, and so the orbit of the motion of the planets will be a plane. And this analysis is valid for planets and for satellites around the earth, including the moon, which is a natural satellite, and the artificial satellites. So in planetary motion, the areal velocity is equal to j by 2m is a constant, or the area swept out by the radius vector is a constant in constant interval of time. Or we can say that the rate of seeping out of the area by the radial vector from sun to the planet is a constant. In another way, we can say that the area swept out by the radius vector in equal intervals of time are equal, and this is called the Kepler's second law of planetary motion, and this law is valid for artificial satellites moving around the earth. In that case also, angular momentum and areal velocity are constants of motion. So the constancy of angular momentum gives the fact that planets must move faster at the point of closest approach. Here, when the planet is moving from this point to the second point, say in a time t seconds, suppose the same planet is moving from this point to this point by the same time t seconds, then Kepler's law, or the constancy of angular momentum, says that the area swept out by the radius vector should be same. That is, these two shaded regions should be same. It means that the planet moving, when the planet is moving farther away from the sun, the velocity will be small. But when the planet is moving near to the sun, the velocity will be very high, or the speed of the planet will be very high. So the speed of the planet will be very small. The smallest speed will be there when the planet is at the farthest point from the sun. And when the planet is at the closest to the sun, the speed will be maximum. So at these points, the closest point is called perihelion and the farthest point is called aphelion. So at these 2 points, the angular momentum can be taken as mvr, because here the velocity is tangential to the orbit and r is perpendicular to the orbit. Here also velocity is tangential and r is perpendicular. So at both these minimum and maximum points, v and r are perpendicular, so angular momentum can be called as mvr. But this formula mvr cannot be applied for other points, because at these points velocity v and r are not perpendicular. So at the positions of shortest and farthest points, say if r1 v1 and r2 v2 are the positions and velocities at these points respectively, then conservation of angular momentum says that m r1 v1 is equal to m r2 v2, or r1 v1 is equal to r2 v2, or we say that as at the position of minimum, that is at perihelion, r1 is minimum, so v1 should be maximum. At aphelion, r2 is maximum, so v2 will be minimum. So this is another conclusion obtained from the conservation of angular momentum in the case of planetary motion. Now after watching this video, we should be able to answer the following questions, like what is meant by the central force? Prove angular momentum of a particle moving under central force is constant. Define areal velocity of a particle moving in a central force. Then Kepler's second law of motion. Give a qualitative comparison of the speed of Earth around the sun and the positions of aphelion and perihelion. So thank you for watching this video.